Physics teaches us that every body tends to remain at rest until an external force acts upon it. The same happens with the mind. It tends toward inertia. If you don't apply the right kind of stimulus, it will always seek the easiest path: distraction, repetition, the illusion of memorization. But when you apply the necessary force, even if it's small, you set movement into motion, and that movement can grow until it becomes unstoppable. Here's the secret. The brain responds far more to small, consistent impulses than to big bursts of energy followed by quitting. It's like pushing a heavy rock at the beginning. The effort seems overwhelming, but once it starts rolling, physics itself works in your favor. That is the power of habit, transforming repeated actions into accumulated energy until your mind becomes a system that moves almost on its own, with far less conscious effort. Behind every thought lies a mechanism shaped over millions of years of physical evolution. The brain was not designed for success. It was designed for survival. It was shaped to avoid danger, to conserve energy, and to repeat the patterns that kept our ancestors alive. But here's the crucial point. Physics allows transformation. The same laws that govern force, friction, rhythm, and leverage can be used to redesign your habits, your focus, and your productivity. The biggest mistake is believing that simply wanting it badly enough is enough. Left to itself, the mind seeks comfort, shortcuts, and excuses. But the very principles that make it conserve energy can be hacked to release power. Reduce unnecessary friction, distractions, repetitive decisions. Create leverage, triggers that multiply minimal effort, and establish rhythm, cycles that generate consistency. When you master these three forces, you create an environment where the right action becomes the path of least resistance. Learning means simplifying down to the essential. If you can't explain something clearly, you haven't truly understood it. When you translate a complex idea as if you were teaching it to someone younger, you strip away the noise, uncover gaps in your reasoning, and create smooth surfaces for thought to flow. That clarity is not just intellectual. It transforms behavior because it illuminates the exact next step. Transformation is not mystical. It is mechanical. You will learn to position points of support, internal and external levers, to smooth out surfaces, remove friction that slows you down, to establish cadence, the rhythm that sustains action, and to build radical clarity, simplicity that reveals the essential. From now on, treat your mind as a physical system. Design, test, measure, refine. That is how you create, with rigor and elegance, a successful mind. Now, picture your mind as an electrical circuit. Every negative thought is like resistance, reducing the flow of energy. Every focused thought is like a clean conductor, letting the current run stronger. When you eliminate noise, useless worries, limiting beliefs, digital distractions, you reduce resistance and increase the power of your own mind. Clarity becomes the perfect conductor, and the result is absolute focus. Physics also shows us the importance of frequency. A steady wave can break through any barrier given enough time. In the same way, when you repeat a practice every day, no matter how small, you create mental vibrations that shape your identity. It's not about brute force. It's about rhythmic consistency. That's why just 10 minutes of daily reading can be more transformative than a single marathon study session. Now, imagine applying this vision to your own brain. You create movement when the mind wants to stop. You channel energy through the paths of least resistance. You establish frequency and rhythm until your identity rewrites itself. This is the invisible engineering of success. It's not about thinking positive. It's about using the very laws of physics to transform your mind into a field of creative energy. When physics meets discipline, the mind stops being a weight that holds you back and becomes the lever that launches you into the future you desire. And here lies the key. Gravity is the invisible force that keeps planets, stars, and galaxies in orbit. Nothing escapes its field of attraction. The The same thing happens inside your mind. Every thought you repeat generates a gravitational field that pulls new ideas, emotions, and behaviors in the same direction. If you think small, you create a narrow orbit. If you think big, you expand the universe around you. Pay close attention now, because this is one of the greatest secrets of transformation. Your mind always attracts what resonates with your dominant thoughts. Constantly thinking about failure creates a field where opportunities seem to vanish, as if sucked into a black hole. But focusing on discipline, abundance, and learning generates positive gravity that attracts people, ideas, and paths that once seemed invisible. That is why you must carefully choose the direction of your mental orbit. Negative gravity is treacherous. Thoughts of doubt, fear, and comparison pile up until you become a prisoner of them. But positive gravity is born when you deliberately choose to plant thoughts of action, purpose, and confidence. At first, it's like a small star, fragile, still forming. But as you feed it with consistency, that field grows so strong that everything in your life begins to align with its energy. Now imagine yourself as a planet that can break free from a toxic orbit and enter a new trajectory. To do that, you need escape velocity, and that force is created by the daily repetition of new thoughts until they become stronger than the old ones. It's like igniting a sun inside you. Your gravity changes, your light grows, and what once seemed impossible begins to orbit naturally around you.
Understand this. You don't attract what you desire just once. You attract constantly what your mind feeds on every single day. If you sustain focus, discipline, and a clear vision, you generate a gravitational field so powerful that nothing can stop your rise. And when that happens, it's no longer you chasing victory. It's victory being pulled into your orbit. Just as coal only becomes a diamond when it is subjected to enormous pressure, your mind only reaches its strongest form when it faces resistance. It is in friction, in tension, in moments of weight, that the brain stops being just a machine of survival and begins to forge itself into a mind of success. To run away from pressure is to waste the chance to become something rare and valuable. Picture steel being tempered by fire. First, it is heated until it nearly breaks, then plunged into extreme cold to gain hardness. That cycle of extremes is what gives it incomparable strength. The same is true of your mind. Every challenge, every criticism, every apparent failure is part of the forging process. Pain does not come to destroy you, it comes to shape you. Mistakes are not signs of weakness, they are the raw material of growth. Most people chase comfort zones, forgetting that prolonged comfort weakens the mind. Muscles grow because they are subjected to tension, and the mind expands when it is challenged. When you face a problem that feels larger than you, you are actually stretching your limits. And every time you return stronger, you are proving that pressure doesn't destroy you, it polishes you. Now, picture yourself as a diamond in formation. At first, you look like nothing but formless coal, common, dull, without shine. But when life puts you under pressure, debts, criticism, doubt, loss, you face two choices: to shatter into pieces, or to allow that weight to mold you into an unbreakable structure. The secret is not to resist pressure, but to accept it as an inevitable part of becoming extraordinary. Remember, every obstacle is an invitation to growth. Every voice that doubts you is fuel to prove it wrong. Every fall is the exact moment your mind is being strengthened. It's not about enduring passively, but about transforming each impact into energy, each blow into refinement, each challenge into evolution. This is how you forge, under fire and weight, a mind capable of conquering any victory. Richard Feynman had a simple technique, yet powerful enough to turn any ordinary mind into an extraordinary one. He said that if you truly understood something, you should be able to explain it clearly, even to a child. It seems simple,
but it is the master key that opens all doors. When you force yourself to simplify, you expose the holes in your reasoning. You uncover what you really know and what you still need to learn. That is the first secret. Clarity is power. The brain loves to deceive itself, pretending it understands just because it memorized some fancy words. But when you practice simple explanation, you hack this mechanism, strip away the illusions, and force the mind to build real connections. That's how learning becomes solid and creativity begins to flourish. And this technique is not just for students. It's for anyone who wants to master their own life. Physics also teaches us that every system can be modeled, tested, improved. Your mind is no different. You can create movement when it wants to stop, overcoming inertia. Reduce the friction that holds you back, eliminating distractions. Use frequency to your advantage, daily habits, and generate positive gravity that attracts opportunity, dominant thoughts. And when pressure comes, instead of breaking, you remember, it is fire that turns steel into a sword, and pressure that turns coal into diamond. Now imagine applying Feynman's technique together with these principles of physics. You simplify your goals until they are crystal clear. You test each small action as an experiment. You discard what doesn't work and reinforce what does. In this way, the mind stops behaving chaotically and begins to operate like a system of precision. And the result is inevitable: discipline, focus, productivity, and success. Remember, your brain was not built for success, but for survival. Yet when you apply the principles of physics and the clarity of Feynman's technique, you reprogram the machine. You create a mind that learns faster, acts with confidence, attracts what it desires, and grows stronger with every challenge. That is the path to true transformation, using the science of life to forge an invincible mind, a mind of success. Pay close attention now. In physics, there is a relentless law called entropy. Everything, inevitably, tends toward chaos, and your mind is no exception. Without discipline, it scatters, loses focus, and is carried away by any distraction. That's why so many start with enthusiasm and end up empty, because they never created structures to sustain order. But here's the key. Routines and rituals are the antidote to mental collapse. Picture your mind as a house. If you don't clean it daily, dust piles up, objects get lost, confusion takes over. With the brain, it's the same. A daily reading habit, a fixed time to plan, a moment of silence before beginning work. Every small gesture creates order in the midst of chaos. And the more order you build, the more free energy you have to create, to decide, to act. Discipline doesn't limit you, it sets you free. Now think with me. When one frequency meets another, both begin to vibrate together. This is the principle of resonance, and your mind works exactly the same way. If you surround yourself with negative people, shallow content, mediocre ideas, your frequency drops and you vibrate at that same level. But when you connect with brilliant minds, powerful words, and inspiring content, your mind resonates at a higher, stronger frequency. But if you connect yourself with brilliant minds, with powerful words, with content that lifts your vision, your mind begins to resonate at another frequency, higher, stronger. That is why choosing what you consume is choosing who you become. Every book you read, every conversation you have, every video you watch is a tuning. And when you adjust your mental dial to the frequency of success, you inevitably begin to vibrate like the greats. Remember, you don't need to be physically next to geniuses. You only need to be in contact with their ideas. That alone is enough for your mind to learn to vibrate as they do. And here lies another secret, the domino effect. A small action triggers a chain reaction. Never underestimate the power of a minimal habit. 5 minutes of study can multiply into an hour of focus. A simple act of gratitude can open the door to an avalanche of positive thoughts. A quick walk can trigger a wave of productivity for the rest of the day. The mind loves continuity, and every domino you push starts a flow that can completely transform your life. Now picture the universe. It does not stop. It does not shrink. It does not retreat. It is always expanding, and so must your mind. When you stop learning, stop questioning, stop challenging yourself, it's as if you were going against the very nature of the cosmos. But when you open yourself to curiosity, to new questions and new answers, your mind expands, grows, occupies territories that once seemed unreachable. Stagnation goes against the natural order of things. Growth is not optional, it is a necessity. And this growth doesn't come from having all the answers, but from never stopping to ask. Every new doubt is like a galaxy forming. Every discovery is a star lighting up in the infinite space of your consciousness. Remember, physics shows us that the universe moves forward, always expanding. Therefore, align your mind with that same movement. Expand your vision, expand your limits, expand your courage. Because when the mind grows without ceasing, the entire life grows along with it. And at that point, you become unstoppable, a universe in expansion, capable of attracting, creating, and transforming everything around you. Now I want you to commit to your mind. Write in the comments, "I decide to evolve every day." That will be your decree to keep expanding your mind daily. If this video spoke to you, like it, subscribe, and turn on the notifications to continue receiving content that transforms. Thank you so much for your attention, and see you next time.
Dark matter often sounds confusing because the name suggests something strange or unknowable. In reality, the idea grows out of very ordinary observations about motion and gravity. Nothing about it starts with mystery for its own sake. It begins with careful measurement and a simple question: does what we see account for how things move? Consider a galaxy as a vast system of stars orbiting a common center. Gravity provides the attraction that keeps those stars bound together. By measuring how fast stars move at different distances from the center, it becomes possible to estimate how much mass must be present. This approach works reliably for familiar systems, such as planets around the sun. When astronomers applied the same reasoning to galaxies, something unexpected appeared. Stars far from the center moved much faster than a visible matter could justify. The stars' gas and dust that telescopes revealed did not provide enough gravitational influence to explain the motion. The galaxy behaved as though it contained much more mass than could be seen. At first, this seemed like a measurement problem. Instruments improved, data sets expanded. The result remained. The same mismatch appeared across many galaxies, and later in large collections of galaxies. Motion consistently pointed to additional mass spread well beyond the bright regions. At that point, the issue could not be dismissed. Either gravity behaved differently on large scales, or a large amount of matter influenced motion without interacting with light. Dark matter enters as a name for that missing influence. The term does not describe what it is made of, it describes how it behaves. It refers to whatever produces gravitational effects without emitting or absorbing light. This way of thinking fits naturally within physics. Physical existence does not depend on visibility. It depends on measurable influence. Long before air was understood, its effects on motion and pressure made its presence undeniable. Dark matter occupies a similar logical role, though on cosmic scales. Evidence extends beyond galaxy rotation. Light passing near massive clusters bends more than visible matter alone predicts. The large-scale structure of the universe forms in ways that require additional gravitational influence early in cosmic history. Each observation points to unseen mass shaping space and motion. A deeper question follows naturally. Does this unseen influence come from a new kind of matter, or does it signal a need to revise how gravity behaves across vast distances? Both ideas aim to explain the same observations. Understanding dark matter begins with accepting that gravity responds to mass whether that mass shines or not. Following that influence carefully leads deeper into how matter, gravity, and the structure of space itself fit together. Following that influence leads straight into how dark matter becomes more than a label and turns into a measurable part of modern physics. One of the clearest moments came in the 1970s through the work of astronomer Vera Rubin, working with Kent Ford. Rubin studied how stars move within spiral galaxies. According to gravitational reasoning that works everywhere else, stars farther from the center should move more slowly, much like distant planets around the sun. What Rubin found refused to follow that expectation. The outer stars moved at nearly the same speed as inner ones. The motion traced a flat curve rather than a declining one. That result carried sharp implications. Either gravity changed its behavior at galactic scales, or far more mass surrounded the galaxy than telescopes revealed. Rubin's careful measurements, repeated across many galaxies, pushed the idea of unseen mass from speculation into necessity. From there, the concept grew stronger through independent methods. One of the most striking involves how massive objects bend light. Einstein's description of gravity predicts that mass curves the paths of light traveling nearby. Astronomers use this effect, called gravitational lensing, to map where mass resides. In the early 2000s, observations of a system known as the bullet cluster, analyzed by Douglas Clow and collaborators, showed something remarkable. Ordinary matter, visible as hot gas, slowed and piled up after a collision between two galaxy clusters. The gravitational influence traced by lensing appeared somewhere else entirely. The dominant mass passed through with little interaction. That separation mattered. It showed that the unseen mass behaved differently from familiar matter. It clumped gravitationally, yet barely interacted through collisions or light. Gravity revealed its presence even where visible matter lagged behind. These observations point toward what dark matter represents at a fundamental level. Dark matter functions as a source of gravity that interacts very weakly, if at all, through other known forces. It contributes mass energy to space, shapes motion, and influences how structures form, while remaining largely indifferent to light, heat, and ordinary collisions. This challenges everyday assumptions deeply. In daily life, matter announces itself through sight, touch, resistance, or heat. Mass seems inseparable from substance you can point to. On cosmic scales, that intuition breaks down. Motion responds to gravity alone, not to visibility. A star follows the gravitational landscape laid out by all mass present, regardless of whether that mass glows. Physicists model dark matter using this principle. Instead of asking what it looks like, they ask how much gravitational influence appears necessary at each location to account for observed motion and lensing. Computer simulations then distribute dark matter in extended halos around galaxies and clusters. When these models evolve forward in cosmic time, they reproduce the large-scale structure seen in surveys, filaments, clusters, and voids arranged in a vast web. This success matters. It shows that treating dark matter as a real component of the universe leads to consistent predictions across independent observations. The same invisible mass explains galaxy rotation, cluster dynamics, lensing maps, and the growth of structure from the early universe. At the deepest level currently accessible, dark matter represents mass that participates fully in gravity while remaining largely disconnected from electromagnetic processes. It behaves as matter in the gravitational sense, contributing to how space responds and how motion unfolds, without behaving like atoms, gas, or dust. That realization reshapes how matter itself gets defined. Matter no longer requires visibility, solidity, or chemical structure. Gravitational influence becomes the defining feature. If something shapes motion persistently and consistently, physics treats it as real. This view also explains why dark matter fits naturally into descriptions of space and time. Gravity responds to energy and mass, regardless of form. Space curves, and motion responds based on total content, not on what that content looks like. Dark matter enters those equations seamlessly because gravity already accounts for unseen contributors. What remains uncertain concerns composition. Many candidates exist, ranging from new elementary particles to more complex possibilities. Experiments search for rare interactions deep underground, in particle accelerators and through astrophysical signals. None have yet delivered a definitive answer. What remains firm lies in the gravitational evidence. Dark matter, at this stage, stands as a measured component of the universe, inferred through multiple independent techniques. It represents how much mass must exist for space, motion, and structure to behave the way observations show. Understanding it means accepting that the universe carries substance beyond what eyes and instruments tuned to light can reveal, and that gravity serves as the guide, linking the unseen to everything that moves within it. As dark matter takes its place within physical descriptions, its consequences begin to appear across many areas at the same time. Observations that once felt isolated start to support each other, and familiar ideas about matter, structure, and influence lose their apparent simplicity. The large-scale arrangement of the universe offers one of the clearest examples. Galaxies do not scatter randomly. They collect along immense filaments, surround vast empty regions, and assemble into clusters connected by long strands of mass. Early attempts to explain this structure using only visible matter ran into a timing problem. Ordinary matter, interacting strongly with radiation in the early universe, could not gather quickly enough under gravity to form the structures observed today. Introducing dark matter resolves this tension naturally. Dark matter begins clumping early, before atoms form and before light moves freely through space. It supplies gravitational wells that deepen over time. Ordinary matter later falls into these wells, cools, and forms stars and galaxies. Structure develops in a sequence that matches observation without repeated adjustments. From this perspective, galaxies appear less like independent systems and more like visible highlights tracing an underlying framework. Their shapes, motions, and distributions reflect a deeper mass arrangement that remains unseen. This leads to an unexpected reversal of intuition. Human senses treat visible matter as dominant because it announces itself. On cosmic scales, gravity responds to total mass regardless of appearance. The universe organizes itself according to what contributes gravitational influence, not according to what emits light. Time itself enters the story in a revealing way. The timeline of cosmic evolution aligns far more smoothly when dark matter is included. Small density differences present early on grow at rates consistent with observation. Galaxies form neither too early nor too late. Clusters assemble when expected. A single additional component resolves multiple chronological puzzles at once. Gravitational lensing reinforces this unified picture. Light bends when passing through regions of mass, allowing astronomers to map where gravitational influence resides. These maps repeatedly show mass distributed beyond the boundaries of visible matter. Extended halos surround galaxies and clusters, revealing smooth mass distributions without sharp edges. Here, everyday reasoning begins to fail. Mass feels naturally tied to compact objects with clear boundaries. Dark matter spreads over large regions, forming halos that resist collapse into dense structures. This distribution explains why galaxies remain bound even when their stars move rapidly. The motion reflects the presence of an extended gravitational environment rather than a concentrated core. Another tension arises from how dark matter interacts. In ordinary matter, interactions leave traces: heat, light, friction, radiation. Dark matter interacts powerfully through gravity while remaining almost indifferent to other forces. During collisions between galaxy clusters, ordinary gas slows and heats, while dark matter continues onward, detectable only through its gravitational influence. This challenges assumptions about interaction and causality. Influence often feels inseparable from exchange. dark matter demonstrates that gravity alone suffices to connect systems and shape motion without exchanging light or heat. Causality remains intact because influence still propagates through space, even if it does so through a single channel. A broader picture emerges. The universe resembles a gravitational network in which different components participate differently. Ordinary matter interacts richly through many forces, but contributes modestly to gravity on large scales. Dark matter contributes strongly to gravity while interacting weakly otherwise. Each component shapes cosmic behavior through its own interaction profile. Early skepticism treated dark matter as a placeholder for error. Over time, mismatches appeared repeatedly and independently. Galaxy rotation, lensing, cluster dynamics, and structure formation all pointed toward the same missing contribution. Adding dark matter did not patch individual discrepancies. It revealed a shared cause. This coherence explains why dark matter remains difficult to detect directly. Instruments designed to capture light or heat cannot register something that barely engages with those processes. Its presence must be inferred through motion, lensing, and large-scale structure. Physics already relies on inference in many domains. Gravity itself announces its existence only through effects. This reliance on inference carries an important implication. The universe does not restrict itself to what human senses evolved to detect. Perception samples a narrow band of reality. Physics expands that band by following consistent effects wherever they lead, even beyond direct observation. Dark matter also reshapes how space itself is understood. Gravity links mass energy to the geometry of space-time. If most mass resides in dark matter, then large-scale curvature reflects that unseen contribution. The paths galaxies follow, the way light bends, and the formation of structure all depend on it. This places dark matter at the center rather than the margins of cosmology. The universe responds primarily to what weighs the most, not to what shines the brightest. Computer simulations highlight this point vividly. Models that include dark matter evolve into structures resembling observed surveys, complete with filaments, clusters, and voids. Models that exclude it fail in systematic ways. Structures appear late, thin, or incomplete. Each failure points back to the same missing ingredient. Viewed individually, these observations might invite separate explanations. Taken together, they form a consistent narrative. Motion, lensing, timing, and structure all trace the same gravitational influence. The meaning of dark matter extends beyond accounting for missing mass. It indicates that physical reality includes components operating outside direct detection, shaping outcomes through long-term, large-scale influence. This does not diminish ordinary matter. It places it within a wider context. Stars and planets become visible expressions of deeper gravitational organization. What shines follows what weighs. Understanding dark matter in this way changes how explanation itself works. Instead of relying on appearance, physics relies on convergence. Multiple independent measurements pointing toward the same unseen cause outweigh the absence of direct detection. Dark matter connects gravity, motion, space, and cosmic history into a unified framework. Each reinforces the others. What once appeared as scattered anomalies now reads as different perspectives on the same underlying structure. That realization carries an important implication. The universe remains intelligible even when much of it lies beyond immediate perception. Careful attention to effects leads to coherence rather than confusion. Dark matter does not sit alongside the story of the universe. It runs through it, shaping how matter gathers, how structures form, and how motion unfolds across vast distances. Understanding that thread transforms many isolated puzzles into a connected picture, revealing a universe that proves larger, yet no less ordered than it first appears. When all the pieces are viewed together, dark matter settles into a clear role rather than remaining a loose hypothesis. It provides a consistent way to understand how the universe behaves on the largest scales, tying motion, structure, and stability into a single picture supported by many observations. Galaxies rotate as they do because they sit inside extended regions of unseen mass. Clusters remain bound because additional gravitational influence surrounds them. Light bends along paths shaped by more mass than telescopes reveal. Large-scale structure forms early and grows in the right way because extra gravitational influence shapes space long before stars appear. Together, these facts reinforce one explanation. This convergence marks what physics treats as firmly established. A substantial amount of matter contributes gravitationally across the universe while remaining largely invisible to light and ordinary interactions. Its presence is inferred through motion, lensing, and structure, and those inferences agree across different methods, scales, and eras. Removing this component breaks that agreement. Including it restores consistency. What remains uncertain lies in the details rather than the existence. The exact nature of dark matter remains unknown. Its composition, internal properties, and origin resist direct detection. Experiments search for rare interactions. Observations probe subtle effects. The absence of a definitive identification sets the boundary of current knowledge. This balance between confidence and uncertainty matters. Dark matter does not represent a missing piece filled in by guesswork. It represents a component required by evidence, even as its deeper description remains incomplete. Its strength lies in how many independent observations it unifies without contradiction. Including dark matter reshapes how stability itself is understood. Systems remain intact not only because of what shines within them, but because of what weighs around them. Motion responds to total gravitational influence, not to visibility. Structure follows mass, whether that mass announces itself or not. This perspective alters how familiar scenes are interpreted. The night sky no longer appears as a collection of isolated lights scattered across emptiness. Each bright point traces a deeper gravitational environment shared with countless others. What can be seen marks only a fraction of what governs motion and form. Dark matter also clarifies why the universe remains intelligible. The same principles explain galaxies, clusters, and cosmic structure without changing rules from one scale to another. Gravity responds consistently. Motion follows predictably. Stability emerges naturally. The practical takeaway rests here. Reality extends beyond direct detection, and physics follows influence rather than appearance. Some of the most important contributors to how the universe behaves do not announce themselves through light, heat, or touch. They reveal themselves through what they shape over time. Understanding dark matter encourages a broader view of existence. What matters most is not always what stands out, but what holds everything else together. The universe evolves under the guidance of influences that operate indirectly yet persistently, shaping motion, structure, and history across vast distances. Seen this way, dark matter stops feeling distant or abstract. It becomes part of the framework that allows galaxies to form, motion to remain stable, and the universe to develop structure at all.
Let's talk about something that sounds ordinary, almost boring, yet sits underneath nearly everything physics says. The idea of a state sounds like a condition, a description of how something is right now. But in physics, it carries a precise meaning. A state is the full physical situation of a system written in the smallest amount of information needed to determine what can happen next. Physics has a strict rule here. It does not care about how a system arrived where it is. It only cares about how it is right now. If two situations are physically identical at this moment, physics treats them as the same, even if their histories were wildly different. A short example makes this concrete. Think about a cup of coffee on a table. To predict what happens next, physics does not need to know who brewed it, what cafe it came from, or how tired you are. What matters is whether it is hot or cold, how much coffee is there, and the surrounding room temperature. If two cups match in those properties, physics predicts the same cooling behavior for both. The story behind them disappears. Only the present description remains. That present description is the state. This idea reaches far beyond coffee. A moving ball, a gas in a room, a planet in orbit, all of them are treated the same way. Physics asks a single question: what information is required to fix the future behavior? Everything else is ignored, not out of laziness, but because it has no physical effect. This is where people often hesitate. It feels like something must be missing. Surely, reality carries more detail than a short list of numbers, yet experiments keep agreeing with physics. If a detail cannot influence what happens next, it does not belong in the state. A state is not a photograph. It is a working summary. It contains exactly what the laws of nature can act on and nothing more. That makes states powerful and also a little unsettling. It means the universe carries itself forward moment by moment without consulting its past, except through what the current state already holds. Everything that can happen next depends on what fits into that description and nothing else. So, let's slow this down and take it apart carefully, because this is where the word state stops sounding ordinary and turns into something precise. At the most basic working level, a state is the complete physical condition of a system, expressed in a form that allows the laws of physics to operate without guessing. It is not a picture, not a label, and not a story. It is a set of facts that fully fixes what the system can do next. That word complete is doing real work. Here, complete does not mean detailed in a human sense. It does not mean rich, expressive, or emotionally satisfying. It means that if you hand this description to the laws of physics, they do not ask for anything else. No extra information, no missing inputs, no follow-up questions. Some detail can affect what happens next. It belongs in the state. If it cannot, it does not. That rule sounds obvious until you apply it. Seriously, return briefly to the coffee. Suppose two cups sit on the same table. One was brewed 5 minutes ago, the other an hour ago. One was stirred clockwise, the other counterclockwise. One came from a cafe, the other from a kitchen. None of that enters the state if the temperature, the amount of liquid, and the surrounding air are the same. Physics predicts the same cooling behavior. The rest feels important to us, but it has no physical leverage. That difference between what feels real and what can influence future behavior is where many people get lost. Physics has learned to be ruthless about it because prediction depends on it. This tells us something crucial about what a state actually is. A state is not how things look, it is how things are. Positioned relative to the rules, that is a very different notion. It trades rich description for functional sufficiency. This is why states so often look like a short list of numbers, not because reality is simple, but because most details cancel out when it comes to future change. People often expect that. More description should always improve. Prediction, Physics finds the opposite. Extra description often adds noise. Without adding power, states are minimal on purpose. Now, follow the consequences of that idea. Any change you can think of, motion, heating, mixing, decay, growth, can be described as a transition from one state to another. The laws of physics are nothing more than rules that map one state into the next. This reframes the entire structure of physics. Instead of objects being pushed around by laws, you get states being updated by rules. Instead of causes acting on things, you get present conditions fixing future conditions. Take memory. People often speak as if physical systems remember their past. Physics says something stricter. Any trace of the past must be encoded in the current state. If it is not encoded there, it has no effect on what follows. A stretched spring carries information about being stretched because its present shape contains it. A scar carries information about an injury because the tissue structure contains it. A cooled cup of coffee carries no information about how hot it was an hour ago because nothing in its present condition encodes that fact. Memory in. Physics is not a mysterious faculty. It is information stored in a state. Leads to a result many people resist. The past has no direct influence on the present. Its influence exists only through what survives in the current state. If nothing survives, the past is physically silent. This is not a philosophical preference. It is forced by how prediction works. If two systems share the same state, physics gives them the same future. No experiment has ever contradicted this. Now let's push deeper into what a state is, not just how it behaves. A state is an abstract object. That word often raises eyebrows, but here it means something very specific. The state is not located in space the way the system itself is. System exists in space. The state exists in the space of possible conditions. Those are different arenas. A ball travels through space. Its state lives in a mathematical space whose coordinates represent position and motion. A gas fills a room. Its state lives in a space defined by quantities. Like temperature, pressure, and density, the system and its state are related, but they are not the same thing. This distinction becomes important as systems grow large. A gas contains an enormous number of particles, far too many to track individually. Still, it has a state. Physics uses collective quantities because they preserve predictive power. The full microscopic detail exists, but the state that physics actually uses is compressed. This reveals another sharp lesson. A system always has a state, even when no one can write it down. Existence and accessibility are not the same. Weather has a state. We measure parts of it, approximate others, and still get surprises. The laws did not fail. The description was incomplete. This reframes uncertainty in a very concrete way. Uncertainty is not something floating over reality. It is a mismatch between the actual state and the state we are able to specify. Physics never becomes confused. Descriptions do. This also explains why physics places so much emphasis on initial conditions. Laws by themselves do not produce specific outcomes. They only specify how states change. Without a state to act on, laws describe possibilities, not events. People often ask why the laws of physics do not explain everything. The answer is blunt. Laws do not select states. They transform them. The universe does not. Ask the laws what state to be in. It already is in one. Now bring this picture into modern physics. In quantum mechanics, the state takes a form that resists everyday language. It does not assign definite values to properties like position or motion. Instead, it encodes the full structure of possible outcomes, yet its role remains unchanged. The quantum state still contains everything physics can say about what follows. Nothing extra can be pulled from it, nothing less will. Suffice, this result bothered many brilliant physicists. They suspected hidden layers beneath the formalism. Decades of experiments answered the same way. Predictions match the quantum state exactly, and no hidden layer reveals itself. Once again, physics encountered the same lesson. Reality provides exactly the information it uses, and no surplus. Here the idea of a state stands out as more than a technical detail. It holds the structure of physics together. The universe advances by carrying forward a compact description of itself. Each moment inherits on lie what the present state contains. Everything else drops out of physical relevance. This does not make reality thin. It makes it efficient. And now something subtle but powerful comes into view. If the state contains all that can influence what follows, then the question what exists quietly transforms into what can affect future change. In physics, existence and influence are inseparable. That single move explains why some things that feel important never appear in equations, while some abstract symbols carry enormous predictive force. Physics follows influence, not impression. State is not jargon at all. It is the mechanism by which nature carries information forward in time. And with that backbone in place, a further tension comes into view, one that appears when the very notion of a single, definite state begins to strain under it. From here, the idea of a state stands at the center of how physical influence is organized. If influence must pass through the state, then anything that fails to register there cannot affect what follows. This draws a hard boundary around explanation. Physics does not ask what might have played a role. It asks what is encoded right now in a way that constrains the next moment. This changes how cause and effect are treated. Causes are not events reaching forward from the past. They are features of the present state that limit what can happen next. Effects are not produced by history pushing forward. They are produced by rules acting on current conditions that view clashes with everyday habits of thinking. People tend to place causes in stories about what happened earlier. Physics places them in the present. Description. Difference is structural, not linguistic. Now look at systems where states react strongly to small differences in chaotic dynamics, extremely tiny. Variations in the state lead to wildly different outcomes. Weather illustrates this well. Two atmospheric states that differ by amounts far below any practical measurement can lead to entirely different futures. The rules remain exact. Nothing about the laws breaks. The difficulty lies entirely in the state itself. Here is the striking result. Rule-based evolution survives. Even when prediction fails, the system follows its laws perfectly. Yet, foresight collapses because the state cannot be specified with enough precision. Unpredictability in this sense does not signal disorder. It signals sensitivity. This separates two ideas that are often mixed together. Lawfulness describes how states lead to states. Predictability describes whether those transitions can be tracked with the information available. One can hold without the other. Now move to smaller scales. Quantum physics accepts the same framework and then stretches it in a way that defeats familiar expectations. The quantum state does not list properties as fixed facts. It does not supply a definite position or motion ahead of interaction. Instead, it encodes how the system can respond when interaction occurs. This is not vagueness. It is precision of a different kind. The quantum state contains everything that can shape outcomes. It simply refuses to supply values that have no physical role until interaction takes place. This leads to One of the most surprising consequences. In physics, the same state can give rise to different outcomes depending on how it is probed. The outcome is not stored in advance. It is selected through interaction. For a long time, many physicists expected a deeper layer that would restore familiar descriptions. Experiments repeatedly blocked that route. Predictions drawn from the quantum state matched reality exactly, and no hidden layer ever showed itself. Here, the meaning of a state sharpens. Further, it is not a list of attributes, it is a constraint on possible futures. Nothing outside that constraint appears. In outcomes, this reworks causation again. There is no side channel through which influence travels beyond the state. No invisible mechanism supplements it. Influence passes forward only through what is, encoded at each moment. This also explains why higher level sciences remain valid without conflict. Chemistry, biology, and neuroscience all describe states, just not microscopic ones. A chemical state summarizes bonding arrangements. A biological state summarizes metabolic activity. A neural state summarizes electrical and chemical activity across networks. Each level tracks influence relevant at its scale. None violate physics because each respects the same rule. Future behavior is limited by present. Conditions reduction does not erase these descriptions, it anchors them. Now a natural puzzle emerges. If states carry everything relevant and if laws act uniformly, why does the future ever feel open? Why does novelty appear at all? The answer lies in complexity rather than indeterminacy. Even systems governed by strict rules can generate behavior that resists anticipation because the space of possible states is enormous. Rules apply locally, but they're repeated. Action produces outcomes that exceed simple forecasting. Nothing extra is added. What already exists rearranges itself in ways that overwhelm tracking. This explains why surprise persists even in a lawful universe. Surprise reflects limits on access to states, not failures of the rules. At this stage, the idea of a state carries weight beyond calculation. It implies that reality advances by carrying forward exactly what can influence what follows, no more and no less. The universe operates with strict economy. That economy explains both the reach and the restraint of physics. Reach comes from focusing only on influence. Restraint comes from ignoring everything else. The picture that emerges is stark, but coherent. Reality is not driven by hidden narratives or accumulated intentions. It proceeds through continuous updates of states under fixed rules. Every moment inherits a complete description of what can shape the next one. Everything else, no matter how compelling, plays no role. This does not strip the world of richness. It explains how richness arises without extra machinery. With this framework in place, one issue stands ahead. Measurement itself must be treated as a physical process subject to the same rules and the same limits. That issue waits just. Beyond this point, measurement brings the framework to completion without adding anything new to the rules. When a system interacts strongly with another system, the two no longer carry separate descriptions. Their physical conditions become linked. From that point onward, there is a single combined description that governs what can happen next. This is not a special category of event. It is the same kind of update that occurs in every physical process. Measurement does not reveal a pre-written answer. It creates a new situation by coupling systems together. This fact removes a long-standing confusion. There is no divide between natural evolution and observation. Both are physical interactions. Both follow the same laws. Both operate by updating states. With that, the picture closes cleanly. Physics rests on a small set of claims that have survived every test placed against them. Every physical system carries a complete description of its current condition. The laws of physics operate only on that description. What happens next depends only on that description and the laws. Anything not present in that description cannot influence future behavior. These statements are not philosophical positions, they are the conditions required for prediction, explanation, and consistency to function at all. There is also a crucial distinction that keeps reappearing across physics. A system can have a well-defined description even when no one can specify it fully. Limited access restricts forecasting, not the behavior of the system itself. Nature does not wait for complete information in order to proceed. This explains why lawful behavior continues even in situations where outcomes appear surprising or irregular. There are also boundaries worth stating clearly. Physics does not claim that current descriptions of states are final. Classical descriptions were replaced by quantum ones. Future theories may alter the form again. What cannot be removed is the role these descriptions play. They carry all physically relevant influence forward. Physics also does not claim to explain why the laws take their particular form. States describe how change unfolds under given rules. The origin of those rules remains beyond experimental reach, and physics does not require a single, uniform description across all scales. Instead, it supports compatible descriptions at different levels, each tracking influence appropriate to its domain. These limits are not weaknesses. They define where physics is precise and where it remains silent. Now assemble the full view. The universe is not best captured as a collection of objects accumulating properties through time. It is better captured as a continuous progression of physical conditions, each one determining what can follow. Laws act as update rules, transforming one description into the next. Nothing outside that process plays a role. This explains why physics favors compressed descriptions, explains why distant histories fade while present conditions dominate. It explains why chemistry, biology, and neuroscience coexist without conflict, each using descriptions suited to their scale while remaining physically grounded. It also explains why explanation has sharp limits. Physics can state what follows from what and what cannot follow at all. It does not promise narrative satisfaction. It promises internal consistency. The takeaway is direct. Reality advances by carrying forward only what can influence what comes next. If something shapes the future, it appears in the current description. If it does not appear there, it has no physical effect. That single principle replaces countless informal assumptions with one disciplined framework. The world, then, reads not as a build-up of past events, but as a continuous handoff, each moment passing forward exactly the information required for the next and nothing beyond.
The greatest obstacle to building a reliable mind isn't lack of effort. It's that most people are building the wrong thing entirely. Watch someone preparing for an examination. They sit with their textbook open, reading the same paragraphs over and over. They copy definitions onto index cards. They highlight sentences until the page looks like a rainbow. Hours disappear into this work. But what's actually being constructed inside their mind? They're creating the illusion of knowledge. The words become familiar. The equations start to look comfortable. There's a warm feeling of recognition when they see the material again. And this feeling is treacherous because it masquerades as understanding. The brain confuses familiarity with comprehension, and the student walks into the examination room believing they know something, only to discover they know nothing at all. Most people treat their minds like storage containers. They pour information in, hoping it will stay there, available when needed. They memorize formulas, collect facts, and believe that repetition will somehow transform these fragments into understanding. But a mind built this way is brittle. It can recite information, it can pass certain tests, but when confronted with a genuinely new problem, something it hasn't seen before in exactly that form, it shatters. The mind that can't fail isn't built through accumulation. It's built through a completely different process, one that looks nothing like what most people call studying. The real test of knowledge isn't whether you can recognize the right answer when you see it. The real test is whether you can generate the answer from nothing, using only the principles you understand. And that requires a fundamentally different kind of structure in your mind. Think about the difference between a photograph and a map. A photograph captures what something looks like from one angle, frozen in time. It's detailed, it's accurate for that specific view, but it's also completely rigid. Change your position slightly, and the photograph becomes useless. A map, on the other hand, is an abstraction. It shows relationships, connections, the underlying structure of a territory. With a good map, you can navigate from any starting point to any destination, even through routes you've never traveled before. Most people build their minds like photograph albums. They collect images of solutions, examples they've seen, problems their teacher worked through on the blackboard. But when they encounter a new problem, a different angle, they're lost. They flip through their mental photographs, looking for an exact match, and when they don't find one, they have nowhere to go. The mind that can't fail is built like a map. It contains principles, not pictures. It understands the relationships between ideas, the deep structure that underlies the surface details. And this kind of mind isn't built through passive absorption. It's built through active reconstruction. Here's the first principle. Never trust that you understand something until you can build it from scratch. Not recite it, not recognize it, but actually construct it, starting from the most basic elements you're certain about. Suppose you're trying to understand why objects fall at the same rate regardless of their weight. You could memorize this fact. You could even memorize the historical story that goes with it. But none of that is understanding. Understanding means you can start from what you know about forces and motion and derive this result yourself. You can explain why a hammer and a feather, in the absence of air resistance, must fall together. You can work through the logic step by step, and if someone challenges any step, you can defend it or discover your error. This is exhausting work. It's much harder than reading and highlighting. It takes 10 times longer, but it builds a completely different structure in your mind. Instead of memorizing a conclusion, you've built the pathway to that conclusion. And that pathway can be used again, in different contexts, to reach different conclusions you've never seen before. Most students read a chapter in their textbook, perhaps once, perhaps twice. They feel they understand it because the logic seems to flow smoothly as they read. The author has done the work of making it clear, but this is deceptive. The clarity belongs to the author, not to the reader. Close the book and try to recreate that explanation from memory, and you'll discover how little actually transferred to your mind. The difference is between watching someone else think and thinking yourself. When you watch someone solve a problem on a blackboard, their solution looks elegant, even obvious. Of course, you think, that's clearly the right approach. But put yourself in front of a blank page with a similar problem, and suddenly nothing is obvious. The steps that seemed natural when someone else took them now feel impossible to discover on your own. This is why the second principle is essential. You don't understand something unless you can explain it simply, without jargon, to someone who knows nothing about it. This isn't about making things elementary. It's about testing whether you've grasped the essential idea or just memorized the sophisticated sounding words that surround it. When you try to explain something, really explain it, you discover the gaps in your understanding immediately. You reach for a word you've been using comfortably, and suddenly you realize you don't actually know what it means. You start a sentence explaining how one thing leads to another, and halfway through you discover you can't finish it because you don't see how the pieces connect. These moments of confusion are precious. They're showing you exactly where your understanding is false. Most people avoid this discomfort. When they hit a point they can't explain, they skip over it, tell themselves it's not important, or hide behind technical language that sounds impressive but means nothing to them. But this is precisely the point where the mind that can't fail does something different. It stops and refuses to move forward until the confusion is resolved. It treats every gap in understanding as a structural weakness that must be repaired before building higher. Imagine trying to explain to a bright 10-year-old why ice floats in water. You can't use technical terms they don't know. You can't wave your hands and say it's because of density without explaining what density means and why it matters. You have to think through the actual mechanism, the real reason, in terms of concepts you're both certain about. And in doing this, you often discover that your own understanding was more fragile than you realized. The third principle seems backwards at first. You learn something by trying to solve problems you can't solve yet. Not after you've learned the material, but as the method of learning it. This seems impossible. How can you solve a problem before you know how? But here's the crucial insight. Struggling with a problem you can't solve yet puts your mind in a completely different state than passively reading about the solution. When you struggle, genuinely struggle, your mind is actively searching for patterns, testing possibilities, discovering what doesn't work. And this struggle creates a structure, a framework of questions and attempted approaches. Then, when you finally see the solution, or derive it yourself, or read the relevant chapter, that information doesn't land on passive ground. It lands on prepared ground. Your mind has already carved out the exact shape that this knowledge fits into. The understanding is deeper, more permanent, because you've experienced the problem it solves. Compare two students learning the same concept. The first reads the chapter, understands the explanation, then does practice problems to reinforce it. The second looks at practice problems first, struggles with them, fails, gets confused, then reads the chapter. The second student will understand more deeply and remember longer, even though they spent time failing. The failure wasn't wasted time. It was preparation. This is why the sequence matters so much. Most people try to fill their minds first, then apply what they've learned. But the mind that can't fail is built through the opposite sequence. Attempt, fail, understand, then succeed. The failure creates the structure that makes understanding possible. But there's something even deeper happening here. Something about the nature of real knowledge versus the appearance of knowledge. Real knowledge is a living thing. It connects to other knowledge. It generates new questions. It can be applied in situations you've never seen before. The appearance of knowledge is dead. It's a collection of statements you can repeat, but they're isolated, disconnected from the rest of what you know. The way to tell the difference is simple. Can you use this knowledge to think new thoughts? Can you take two ideas you understand and combine them to reach a conclusion you've never been taught? If your knowledge is real, you can. If it's merely the appearance of knowledge, you can't. This is why memorization alone, no matter how thorough, builds a mind that fails. Memorized knowledge doesn't connect to anything. It's like having 1,000 puzzle pieces scattered on a table instead of assembled into a picture. You might be able to describe each piece accurately, but you can't see what they make together. The mind that can't fail is built by constantly making connections. When you learn something new, you don't just add it to your collection. You ask, how does this relate to what you already know? Does it contradict something you thought was true? Does it explain something that previously seemed mysterious? Does it open up new questions? This active process of connection making is what transforms information into understanding. And it's something you have to do deliberately because it doesn't happen automatically. Your mind won't make these connections just because the information is sitting there. You have to force the connections by asking questions, by trying to use new knowledge in different contexts, by testing whether it really fits with everything else you know. Here's something most people never realize. Understanding isn't something you achieve and then possess. It's something you maintain through constant use. Leave a piece of knowledge unused for long enough, and it degrades. Not because you forget it, exactly, but because the connections weaken. The knowledge becomes isolated again, and isolated knowledge is useless. This is why the fourth principle matters. Keep returning to fundamentals, not to memorize them, but to see them more deeply each time. Every time you revisit a basic principle with more experience, you see it differently. You notice implications you missed before. You understand why it's formulated the way it is. You see connections to advanced topics that weren't visible when you first learned it. The student who races through material once, checking off topics as learned, builds a shallow mind. The student who returns repeatedly to core ideas, seeing them anew each time with more context, builds depth. And depth is what makes a mind reliable. When you understand something deeply, you don't forget it because it's woven into the structure of your thinking. Consider how this works with something as basic as fractions. A child first learns that a half means one of two equal pieces. Simple enough. But come back to fractions after learning multiplication, and you see that a half is also the same as dividing by 2. Come back after learning decimals, and you see it's the same as 0.5. Come back after learning ratios, percentages, probabilities, and each time the concept of a fraction reveals new depths. It's not a new thing you're learning. It's the same idea showing different faces depending on what you can now see. This is how knowledge becomes truly yours, not by collecting it once, but by returning to it, reconsidering it, seeing it from new angles as your understanding grows. And this creates something remarkable, a mind where everything connects to everything else, where each piece of knowledge strengthens all the others. But building this kind of mind requires accepting something uncomfortable. You will be confused most of the time. Real learning, the kind that builds understanding rather than the appearance of understanding, lives in confusion. You're confused because you're genuinely thinking about something you don't yet grasp. You're trying to fit it into what you know, discovering it doesn't fit, questioning whether what you knew before was wrong, testing possibilities. Most people flee from this confusion. They want everything to be clear immediately. When they feel confused, they assume they're doing something wrong, that they need a better explanation, a simpler textbook, a more patient teacher. But confusion isn't a sign of failure. It's a sign that real thinking is happening. The mind that can't fail has learned to be comfortable with confusion, to even seek it out. Because on the other side of confusion, fought through honestly, is understanding that actually means something. The student who avoids confusion builds a mind full of statements they can recite but don't understand. The student who works through confusion builds a mind that can think. Here's how this looks in practice. You're reading about a concept that seems to contradict something you learned before. Instead of skipping past this discomfort, you stop. You write down both ideas clearly. You think about whether they really contradict each other or whether you're misunderstanding one of them. You try to find the exact point where they seem to conflict. You work through examples to see which idea holds up. You might spend an hour on this, maybe more. And at the end, either you've discovered that there's no real contradiction, just a misunderstanding on your part, or you've found a genuine error in something you thought you knew. This is slow. It's frustrating. But this is how you build a mind that won't collapse when tested. Because you've tested it yourself, constantly, as you built it. The final element that makes a mind reliable is the willingness to check everything yourself. Not because you distrust teachers or textbooks, but because checking things yourself is how you make knowledge your own. When you're told that 2 + 2 = 4, you can accept it. But have you ever actually thought about why? Not just counted objects, but understood what addition means at a fundamental level, why it has the properties it does. Most people accept enormous amounts of knowledge on authority. Their teachers said it, the textbook confirmed it, it appeared on the examination, so it must be true. And maybe it is true, but it's not their knowledge, it's borrowed knowledge. And borrowed knowledge fails when you need it most. The mind that can't fail contains only knowledge that's been personally verified. This doesn't mean you derive everything from first principles, though sometimes you should. It means you've thought about whether each piece of knowledge makes sense, whether it fits with everything else you know, whether you can see why it should be true. You've made it yours through understanding, not just acceptance. This is the difference between education and training. Training gives you procedures to follow. Do this, then this, then this, and you'll get the right answer. Education gives you understanding that lets you figure out what to do in situations you've never seen before. Training creates minds that work like machines, reliable only when operating within their designed parameters. Education creates minds that can adapt, improvise, think. And here's the beautiful thing about building this kind of mind. Once it's built, it becomes easier to add to it. Each new piece of real understanding makes the next piece easier to grasp, because you have more foundation to build on, more connections to make. The student who builds their mind properly finds that learning accelerates over time. The student who builds on memorization finds that each new topic is as hard as the last because nothing truly connects. The mind that can't fail isn't built quickly. It's built through patient, honest work, through refusing to pretend you understand when you don't, through struggling with confusion until it resolves into clarity, through making connections until everything you know forms a unified whole. And when you've built this kind of mind, something remarkable happens. Problems that would terrify other people become puzzles you can actually solve. Not because you've memorized more, but because you can think. You can take what you understand and use it to figure out what you don't. You can see patterns, make connections, build solutions from fundamental principles. This is what it means to have a mind that can't fail. Not that you'll never make mistakes, but that your understanding is deep enough and connected enough that you can find and correct your own errors. You can trust yourself to think because you've built something solid, something real, something that won't crumble when the pressure comes.